Hi everyone, welcome to this series of presentation on inferential statistics. In this video, we'll talk about chi-square test, written as chi-square in this form. Chi-square test is essentially a workhorse and very powerful tool in statistics, especially for analyzing categorical data. Imagine you flip a coin and wonder if it is fair coin or not. So chi-square test actually helps answer this by comparing what you expect, equal heads. So what do we expect? Equal heads and tails to what you actually observe. So if there is any difference, then chi-square test can tell you that the coin is fair or not. Essentially, this test is used to assess if two categorical variables are related or if there is any significant difference between the observed data and the expected outcome. It is very useful in many fields of mathematics, engineering, medical, pharma, testing drug effectiveness, for example, or analyzing customer preferences and so on and so forth. So let's get started and see the details of chi-square test, how it is performed step by step. So a little bit of Python experience would be handy, and a basic idea about statistics, probability, and probability density function, cumulative density function, and so on and so forth would be very, very useful here. So let's look at some scenarios where the chi-square test is used. For example, you want to investigate if there is significant association between two categorical variables. For example, gender, male and female, and the other categorical variable can be, choice of a particular product, let's say books or so you would like to find out if there is any association between the gender and the product preference. That would be one use case. And similarly, the again, educational research. Here we are talking about, let's say, the study hours per week. Let's say we can define the study hours in terms of low, moderate, and high. Let's say low meaning less than 4 hours, moderate means 4 to 6 hours, and high meaning 6 to 8 hours, something like that. So you divide the data into some kind of a slab or categories, and then you want to measure if that has any impact on the exam score. So exam score also categories. So these are both the categorical variable. Similarly, market research would be another example. You want to investigate if there is any association between the age group of customers and the preference for some devices or television screens or mobile phones or category of any device. So you want to find out the association between two categorical variable, then you chi-square test is the one that we have to use. So let's take an example here. Suppose we want to investigate whether there is significant association between type of mobile device, let's say iOS, Android, or any other, and the choice of applications that we install. Let's say some iOS user may not be interested in social media, or Android guys don't use any games or as such. So you want to find out the association between the two categorical variable. One is the type of mobile device, the other one is type of applications. So let's say we have the data, some observed data, and this is your mobile device type, and these are the application types. And we have 30 instances where the consumers or the customers who had iOS also had games installed, who had iOS also has social media tools installed, let's say 20 of them, and then utilities maybe 10. Similarly, the other type of mobile users, and they have the instances like 15, 25, and 20. So something like a grid or cross-tab data that you need to collect. Now, with that data, we need to build. So this is the observed data. From the observed data, we have to compute the expected data. So essentially, what we need to do a row sum for each of the row, and then we do a column sum for each of the column. Then we go to the next step, and we compute the expected frequency. Before that, we have to set the hypothesis. So what is the hypothesis here? There is no relation. That means the choice of mobile device has nothing to do with the application types. And the alternate hypothesis would be there is significant association. That means a certain type of mobile user would always use a type of application, for example. So it's essential to set the hypothesis in a right way. And the reason we do null hypothesis in this particular manner is based on the principles of no association, no impact, no side effect, no improvement or no degradation of any sort. So we take as if things are status quo. So for example, here, no association between the mobile device user and also the type of applications. So that's the first step that you do. And then with the observed data that we saw in the previous slide, we are going to compute the expected frequency. So for example, here, for this count of 30, what is the corresponding expected value? And that can be obtained by taking a row total, which is going to be 60, and then the column total, which is going to be 55, and divided by the grand total here. And that we repeat it for every cell here. And that's going to give us the expected frequency. So expected frequency is nothing but proportional allocation or proportional expectation of values here. So chi-square is essentially a difference between what you observe and what you expect based on the marginals or row total and the column total. So if there is any difference, or like the values are different in the grid here, that difference will show up in the uh, expected frequency as well. Now, how do we use this both observed frequency and the expected frequency in computing the statistic? So essentially, the intuition behind the expected frequency formula is a proportional allocation. If two variables are independent, then the frequency of occurrences should also be proportional to the product of the probabilities. That's the intuition behind the expected frequency. Row total, column total divided by the grand total. All right, so now we have the observed data, observed frequency, and the expected frequency. We're going to take the corresponding values and then we subtract those, divide by the expected here. So, and then that would be repeated for all the cells. And the value that you get here is called chi-square statistic or test statistic in chi-square tests. So once you compute this, we can then compare the chi-square test statistic in this slide that we get the value here that needs to be computed with the critical value. So, and with this chi-square, we also have to find out the p-value. So we can compare with the p-value with the alpha or significance level. So the analysis here is essentially about comparing the chi-square statistic with the critical value or p-value with the alpha in order to reject or failing to reject the null hypothesis. Now, in between, we have a concept called degrees of freedom, which is what we discuss in the lecture on t-test as well. The same concept of degrees of freedom is also applicable here. So the intuition behind degrees of freedom is same that we discussed in the t-test. The difference is here because we have a row and a column grid, so the values are across the table type of a form. So we need to take one minus of the rows and one minus from the column. So and then you multiply. Suppose we have 5 rows and 5 columns. So it would be 4 times 4, 16 values are free to change. And those free to change values are used by the chi-square distribution, which I'm going to show you next here. So how do we determine the free cells? Essentially, subtract 1 from the column and subtract 1 from the row, multiply them, and that's going to give us the degrees of freedom. That degree of freedom is used in this distribution here. So for example, in this formula for chi-square distribution, the k is nothing but the degrees of freedom. So for a given data set, you will have 1 degrees of freedom, means one value for that particular data set, and that value is used in the chi-square distribution. So what is changing then is we will have different values of chi-square, which is x here, and we will simulate different values of x, and we get a distribution. This is pretty much the same idea we use in uh, Gaussian distribution as well, although the formula is different there. So the properties of a chi-square distribution, it is always non-negative because of this squaring operation that we apply. The shape of the chi-square distribution is dependent on the type of or the value of the degrees of freedom. It is always skewed to the right side because it's going to start with 0. It's not going to be negative. And because of the values of degrees of freedom, the shape will change, which is what I'm going to show you in a moment now. So the mean of a chi-square distribution is going to be the degrees of freedom. The variance is going to be twice of the degrees of freedom. This is statistically found and established. So the impact of degrees of freedom is in terms of the shape and the spread. So if you have a degrees of freedom as 1, then the chi-square distribution is very, very skewed to the right. As the degrees of freedom increases, then the distribution becomes less skewed, and it becomes, or it approximates, a normal distribution. So higher the degrees of freedom leads to a broader spread of data or distribution and better chances, or we have a better situation to accept the hypothesis or reject the hypothesis. Now, using that distribution, we are going to compute the critical value. By using the alpha, we get the critical value, and then we use the chi-square statistic to compare with the critical value. And likewise, we use the chi-square value that we computed in the previous step. Here, this is my chi-square value. From this, we will derive the p-value and compare against the probability, which is basically the significance level of 5%. So these are two methods or two ways to decide whether to accept or reject the null hypothesis. So just a little illustration with degrees of freedom being 1. The distribution is highly skewed, and as you can see here, there is hardly any room for us to make any analysis. So that means the lower the number of cells, lesser our ability to perform the analysis. Now, if I increase the degrees of freedom to 5, for example, now you see you have a better looking distribution, and it allows us more room for performing the analysis. And if we go with slightly more degrees of freedom, then it gives you a kind of a normal distribution, or something like a standard normal distribution, and gives you a lot of room for making a decision. So this is the impact of degrees of freedom on your chi-square distribution. So let's take a look at the Python code and see how different degrees of freedom really impact or give you different shapes of chi-square distribution. Let's take a look at the simple demo here on how changing the degrees of freedom impacts the chi-square distribution. So let's do a simple. So the chi-square distribution or chi-square package is part of your SciPy stats. That is what I'm going to be using. And the categories of data, male and female, and the clothing categories, that means the preference for either, the cloth, jeans, or t-shirt. We would like to find out any association between the two. So let's generate some data here. So randomly, I'm generating some data and put the data in a data frame. So it's like, female and purchase jeans, female purchase jeans again. So these are the instances of the preferences. All right, so randomly created the data. So you need to prepare a cross tab before you feed it to the chi-square package. So, and it's called contingency table. Just the name is used in chi-square literature, contingency table. So just use the same name. So this is the cross tab that you just obtain from the data set. Now, chi-square contingency is the name of the library which performs the chi-square test. It's going to return the chi-square statistic and a p-value. So it returns a statistic of 5.02 and the p-value of 0.24, which is less than 0.05, and that means we can reject the null hypothesis. What is the null hypothesis here? The gender has nothing to do with the clothing preferences, and that we will reject it. That means the gender has a lot to do with clothing preferences. So let's now attempt the distribution. So let's take the distribution from 0 to 30 just to simulate. And then we obtain a PDF from the chi distribution. And and similarly, we get the critical value for, sorry, the alpha. And that's my critical value, 3.84. So let's plot all of these things together. So this is my chi distribution, and here is the blue line, which is my alpha, 3.84, and a chi square is 5.03. That means which is ahead of the threshold, and that means you can reject the null hypothesis. So 0.02, so this is lesser than 0.05, so you can reject the null hypothesis. So this is the idea behind simple chi-square test. Let's look at the distribution here, how the distribution changes with respect to the degrees of freedom. So this is how the function is going to update the distribution, and then I'm going to choose the degrees of freedom by interactive plot. Let's say I'm choosing here the degrees of freedom 1, and then if I make it, let's say 9, you notice the shape is changing. So higher degrees of freedom, better for us because this allows us more room for making decision or conclusion. Okay, so that was a quick demo on chi-square, um, how to perform chi-square tests using Python and SciPy, and also we looked at the impact of the degrees of freedom on the chi-square distribution. So again, similar example that I showed you in the code here, the female, male, and all, right? And the clothing preferences. And the p-value we obtained was 0.02, which is lesser than the threshold. And if it is lesser than the threshold, you can reject the null hypothesis. The null hypothesis is the gender has nothing to do with the choice of, cloth. So we're going to reject it. That means the gender is dependent or gender does impact the clothing purchase. All right, so and the PDF is from the chi distribution, and once you obtain the PDF, you can find out the cumulative density function, which returns the probability value. Now this is the right skewed, so we just simply take 1 minus of the cumulative density function, and that gives you the p-value, and we compare the p-value with the significance level. So assumptions for chi-square, it can only be used for categorical data, and your observations must be independent. They should not have relations with each other. Expected frequency, researchers say it should be more than 5. If it is less than 5, then it may not be very accurate. Then we have to look at an alternate test called Fisher's exact test. Data should be randomly sampled through a random sampling process, and the categories that we are talking about should be mutually exclusive. They should not have present in both the cases or more than one cases. And the large sample size, like a higher degrees of freedom, is good for our asymptotic validity. So these are the key assumptions here, and we already saw how chi-square is performed. So that's pretty much in the coverage on chi-square tests, a very popular technique in inferential statistics. Thanks for watching. We'll see you in the next video.